So let's go ahead and get started. I'm going to go through the homework, and then I was lazy today, and you know, that's nice for you guys because I didn't actually make a homework for tomorrow, so you know, you have a free day for homework. We'll go through the homework, and then we have some classwork that we've gone through all of the different ways that you can have time-dependent magnetic flux, but there's one way that's it's a little interesting. It's a little bit different. It ultimately ends up being the fact that the area changes as a function of time, but it's not immediately apparent why it is that the area is changing as a function of time. So today's activity is going to go through that example. So to start with, there were two problems that I had given for the homework. The first one was really a Amperes Law question with some Lorentz Force law in it as well. And so this question, you're given some wire that is hollow on the inside, and you're told that some current I flows to the right. And what you want to do is you want to find what the force is on a charged particle Q if it has a velocity of magnitude V0 and was moving along the axis of the cylinder. So you have some particle that's moving like this, some charge Q. And then you also want to find the force on a particle of charge Q if it was outside the cylinder and it's moving with velocity that has a component of V1 in the x direction and a velocity of v2 moving in the y direction or the radial direction, and again this has some charge of q. Okay. So in order to do this, what we want to do is we want to find the force on these two charges. And so that tells us that we want to use the Lorentz Force law. So F is equal to Q V cross B in general plus Q times E. But there's no electric field here. So this term right here is going to be zero. There's only going to be a magnetic field. Okay. So in order to find the force on the first charge, what we need to do is we need to find what the magnetic field is. And because this is an infinitely long wire going in both directions, what we can say is that we have the appropriate type of symmetry in order to apply Amperes law. So Amperes law says the integral of B dot dl is equal to mu naught times I in. And so now what we want to do, we've written down Amperes law. We want to draw some Amperian loops for the regions that we have here. So we were told that this has some radius of A and some outer radius of B. So the first Amperian loop that we're going to draw is going to go around like this. So in order to evaluate this, what we need to do is we need to figure out what the current that passes through this loop is. So for the region where R is less than A, how much current passes through this loop? Zero, right? There's all the current's going through the shell of the cylinder going this way. And so in the region where R is less than A, I in is equal to 0. And so what that says is B is equal to 0. So if B is equal to 0 here, what can we conclude about the force acting on this charge due to the magnetic field? It's also 0, right? So this force right here, so call us F1, is equal to 0. Okay. Now it didn't ask us to do this, but I think it's worth going through just for completeness. To find the magnetic field in the region between A and B, right? We don't actually need this because we're trying to find the force out here, but it's something that's good to do in practice because it's something that we could be asked. Yeah?
But another way to do that would be to basically expand out the Lorentz force, makes the QV B sine n, and sine is 0, since it's in the same plane of the axis?
Well, yeah, in a way that you could say the sine of the angle is 0 because there's no magnetic field to take the angle between, but it's not really that. It's not really because of the Lorentz Force law that the force is 0. It's because there's no magnetic field. Yeah.
So that's where I got using the the Amperes Law. But I'm remembering all those like demonstrations they do where they drop a magnet through like a copper tube or something.
Yeah.
So what's going on?
That's a different scenario actually. So what's happening when you drop a magnet through a tube? So say I have some magnet, so this is like the north end and this is the south end, and I drop it through the tube. This magnet produces a magnetic field, right? And it's non-uniform, right, because it bends like this. So what you can do is you can consider this, this tube really to just be a stack of loops of wire. And as I move this magnet down through this, it's inducing a current in those loops of wire, which in turn produces a magnetic field. So, and that magnetic field is going to oppose the change. So when you do that demo, or when you see it, you do it in an aluminum tube versus a plastic tube. Plastic tube, the magnet just falls right through under the influence of gravity, but when you put the magnet in a conducting tube, it falls slowly. It's because it's inducing a current. So the geometry is similar, but this isn't really the same problem in a sense, because what I'm asking here is I have some charge that's moving, as opposed to here it's a magnet that's moving. Okay. Other questions? Okay. So, like I said, for completeness, it's good to figure out what the magnetic field is in the region between A and B. And so the way that we're going to do that, again, is just to apply Amperes law and draw this Amperian loop here. Okay. So when we do this, we're not enclosing all of the charge, right? Because if I draw this on its side, and this is my Amperian loop, or sorry, it's not all the current, right? It's some proportion of the current. It's not the whole thing. It's less than the whole thing. And so what we need to do here is we need to say that I in is going to be equal to the integral of J dot dA, right? We remember this from when we were doing our circuit analysis and when we were talking about the microscopic form of Ohm's law. So when we look at this equation, we need to figure out what J is. So J, by definition, is just the current density. And so J is going to be equal to the total current, which in this case is I, divided by the total area that the current flows through. So what's the total area that this current flows through?
I times.
Right. So this is going to be pi b squared minus a squared. Okay. So now that we have J, we can plug it in here, and what we see is I in is going to be equal to the integral of I divided by pi b squared minus a squared. dA, what kind of dA do we have here? What is dA going to look like? It's related to it, right? So R dr, there's another factor here. 2 pi, yeah. And again, the reason why this is the case is because we're talking about circular symmetry, right? And so how do we build a total circle from infinitesimal rings that have some circumference 2 pi r? You say that it's going to be 2 pi r times dr. Okay. So now we can evaluate this integral if we put in our limits of integration, and this is where things kind of come back to what we were talking about with Gauss's law when we did insulators. So where does this current start and where does it end? What should my limits of integration be here? A to R, good. So this goes from A to R, right? We can see that because this is the radius of A, this is the radius of R. So when I do this integral, what I end up finding is that I in is going to be equal to I times R squared minus A squared divided by B squared minus A squared. Evaluating the left-hand side of Amperes law is going to give me integral B dot dl is going to be equal to 2 pi r times B. And then we can put the two of these together to find that B vector is going to be equal to mu naught I times R squared minus A squared divided by B squared minus A squared, and this side divided by 2 pi R. And I can throw my theta hat in here to say that it's going around in this direction. Okay. Now, when we're finding the magnetic field in the region that we actually need it, the region outside, we could do this one of two ways. We could do this going through this whole process where we're finding J, but what's another way that we could talk about this? If we're looking at the region now where our Amperian loop looks like this. What's another way that we can say what the current that passes through that is? It's a whole current, right? It's all of the current that goes through here, and that's just going to be I. Right? Could we check that doing it like this?
Yes.
Yeah. So what would we do differently here that would show that we'd actually end up getting the same thing?
Change the balance.
Yeah, we change the limits of integration, right? So if I have my Amperian loop, stop moving this up and down. If I have my Amperian loop out here, now the current is going to go from A to B, and if I change these limits of integration from A to B, this R is going to become a B, and so this is B squared minus A squared divided by B squared minus A squared, which is just I. And so regardless of the way that you look at it, you end up finding that outside of this, this wire, for the region where R is greater than B, the magnetic field is going to be equal to mu naught I divided by 2 pi R, and again times the theta hat. Okay. Now I've been a little bit cavalier with this theta hat and the way that I've been using it, but we'll see what this theta hat really means when we're talking about this force here. So when I want to find what the force is on this particle here, I need to know what the direction of the magnetic field is at the particle. So if the current is going this way, what's the direction of the magnetic field up here? Yeah, you got it. It's pointing out, right? So we finger in the direction of the current, curl in the direction of the magnetic field. And so what that says here is that the magnetic field above the wire is going to be mu naught I divided by 2 pi R pointing out. Okay. So now we can find what the force is acting on this charge. We can break it down into two pieces. So there's going to be some force due to the motion that's going to be up. So let me just draw this again. So there's this V2 and this V1, and we have B pointing out. There's going to be some force from the motion of this particle moving up. There's going to be some force from the motion of the particle moving to the right. So we can actually write this as F1 is going to be equal to Q V1 cross B, and F2 is going to be Q V2 cross B, and then just evaluate these cross products, right? So for the first one, this force is going to be going to the right, so we point our fingers in the direction of the force. Magnetic field curls out, so this is going to go this way. And so what this says is that this force is going to be Q V1 times B as a function of R, whatever the distance is from the center, using this magnetic field, in the negative Y hat direction, right? Because this is this way, like that. Okay. We can do the same thing for this one. So the velocity now is going to be up. So we point our fingers in the direction of V2, and then in order to curl in the direction of in the direction of B, we have to rotate our hand. So this one is going to be Q V2 times B as a function of R times X hat. Okay. Any questions about this? Okay, so let's go ahead and move on to the next one. And so the next one, I should have looked at this a little bit more carefully because I'm actually just not going to do the second part.
I do have a question.
Sure.
So if you were to plug B in, you have R. What is R the distance from? I know we're going from some point of the magnetic field to. Right. So this R is it's just a distance that's radially away from the center here. Okay. So it's just some distance, and it doesn't explicitly say that you're at some distance C from the center, for instance. I wasn't sure if it was going to end up being the center, or if you had to do some integration the distance from all points in the cylinder or something, you know.
No. So and that's kind of kind of, and I'll come back to answer your question. Ask me again if I forget it while I'm explaining this. So the reason why we don't have to worry about what the magnetic field is that's produced from all points is because we used Amperes Law. If we could have done this calculation with B sub r, I would highly suggest you don't do that because it's complicated. It's difficult to parameterize the geometry here in order to use B sub r. So that's why once we figured out what the magnetic field was, we actually kind of don't care what the wire's doing because we have some function that says that for magnetic fields above the wire, I'm going to have, it's going to point like this, and the further I go away from where the wire was, that's what I'm defining R to be. You could say that R is Y, if you're more comfortable with that. The farther away I go, the smaller the magnetic field is. Okay. What was your question again?
Why from the center?
Why from the center? It's because and this kind of goes to the same idea. The magnetic field was defined relative to the center. Yeah. And that's how we ultimately comes down to how is it that I'm drawing the loops. The loops are drawn so that the center of the loop is at the center of the wire. Yeah. Yeah.
Can you explain how you got from the magnetic field being in the angular direction to being
Sure, yeah. So why did I do this to start with? The reason why is, what is the magnetic field really doing? It's going around the wire, right? But the reason why I wanted to say that the magnetic field points out instead of going around the wire is because I need to find what the direction of the magnetic field is explicitly for where the charge is. So this charge it's in the plane of the chalkboard above the wire here. So I need to know what the direction of the magnetic field is here explicitly. It does go around like this, which is why I wrote it generally as this theta hat. But when I do this calculation to find what the force is, I need to know what is the magnetic field where the charge is. And in order to do that, the way that I can find what this is to apply the right-hand rule. So I can point my thumb in the direction of the current. I'm curling around the direction of the magnetic field, which is really what theta hat is defined to be. And then what I'm doing is I'm saying when I'm above the wire in the plane of the board, it's going around like this, and at that point it's pointing out. Is that better?
Okay.
Okay. Other questions? Yeah.
Real quick, am I mentioning again why we know that Fy would be a negative?
Sure. This is just doing right-hand rule again. So fingers in the direction of V1. In order to curl into B, which is out, I have to rotate my hand, and then when I curl, my thumb points down. Yep.
So we don't have to plug in the magnetic field that we found?
No, I mean, I already parameterized it here. So, I mean, this is something that you can do when you're solving problems, that if you don't have to carry around everything that you solve for as long as you've solved for it. So I couldn't just write, this is QVB, because I don't know what B is. But since I've found what B is here, I don't have to plug it in here because I know what it is. Okay. Other questions? Okay, so for the next problem, like I said, I should have looked at this a little bit more carefully because they talk about self-inductance, and I'll talk about self-inductance very briefly, but we're not going to talk about it on the exam. Or we're not going to have self-inductance on the exam. But where self-inductance comes from and why it's going to be important when we do the time-dependent circuits is because when we write Faraday's law, we have the integral of E dot dl is equal to negative partial derivative with respect to time integral B dot dA. But this B here, it's not just the magnetic field that's going through the loop from something that's external to it. It also includes the magnetic field that's produced by the loop itself. So to give you an example, if I have some magnetic field, B as a function of time, is going to be equal to B0 t divided by tau, pointing out. This is going to induce a current that is going to go in this direction. direction, ultimately. You can show that if you go through the whole process. But this current that's induced by this magnetic field produces a magnetic field itself. So there's some induced magnetic field, be induced, that's going to point in. And that's going to be there to oppose the change of this, because this is an increasing magnetic field going this way. Lenz's law says that nature operates in such a way that it opposes change, and so the direction of this current is such that it produces a magnetic field that opposes this increase in magnetic field that's pointing out. Okay. Now, when I'm looking at Faraday's law, this magnetic field is not just this magnetic field. It's both magnetic fields. And so really, when you apply Faraday's law, you get two terms, and you could say that this is B external to think about just this, but then you have to add or subtract an extra term that is related to what's called the inductance. The inductance, and we'll get into this more when we do the time-dependent circuits, but the inductance is kind of like the inertia of the circuit. It's analogous to a mass, ultimately. So the more inductance that you have in a circuit, the harder it is to get charges to move around in it. But like I said, we won't actually worry about this, so I'm going to actually just skip the second part of this question. Okay, so this question says that you have some loop here like this that has a capacitor and some magnetic field B as a function of x, which is equal to alpha plus beta x, and this has some dimensions of h times d. And the first thing that it asks you to do, this is capacitor plates are separated by W, have an area of A. So this capacitance is not explicitly given, but you can find it based on the geometry that it gives you. So it says that the capacitor plates are separated by a distance of W and have an area of A. And so what that says is that the capacitance here is really A epsilon naught divided by W. This is just something from the previous exam. But now we have this capacitance, so that's taken care of. The magnetic field points into the page. So this magnetic field is going to point this way. The first thing it asks us to do is to find what the magnetic flux is. And so we know the magnetic flux is really just, let's go back to our original form of Faraday's law. The magnetic flux is just this term here. So magnetic flux phi sub B is going to be equal to the integral of B dot dA. Because this is pointing in, I'm going to say that dA is also going to be pointing in. And so that also says that dl goes around this way, like that. So when I take this dot product, ultimately this is going to be alpha plus beta x times dA. So what should dA be here? Previously we said dA is equal to r 2 pi r dr. Is it the same here? It's still at 2 pi r dr? Why? Why isn't it this? Yeah, it's not a circle, right? The geometry is different. So what should dA be here?
dx dy.
dx dy, good. So this is dx dy, okay. Now, when we look at the function that we have for our magnetic field, we see that it actually doesn't vary over y. So when we do that integral, we're not, it's just integrating a constant, right? So where does y start?
0.
Yep, y is equal to 0, to y is equal to what? Where does y end? H. Where does x start? X is equal to 0, x is equal to d. Good. Okay, so now we can do this integral here. We end up finding that we're just going to have a factor of h on the outside. This is going to be an alpha times d plus beta d squared over 2. Okay, and that's it. And if you don't follow, it was just some calculus here. You just question?
I think on the answer key it had a negative in there.
That's because of the way they define dA.
Okay.
Ultimately, it'll come out in the wash, but you could have defined dA to go out, and that's actually one of the professors that teaches this always defines dA pointing out. Like I said, there are different conventions that you can use, and that's why it's important to define this, because if I didn't define this, then I don't know which way it should be. Should this be positive? Should it be negative?
That also means the current is going to.
Yeah. So I'm going to potentially have a different sign for my final answer than they're going to have. Okay. Other questions about this? Yeah.
Is this like an example where the area is changing with time now?
It's actually not.
It's not.
It's not. So the magnetic field, and this is a little weird. It's different than, well, no, we have seen things like this. The magnetic field varies with distance, right? But until we say that alpha and beta have time dependency, this magnetic flux is actually time independent. If we said that alpha and beta were just numbers, right? So here, the area is fixed. The area is just staying like this. You could set this up in a way that you would have a changing area if I take this part and I pull it out, so it's moving. But this is just fixed. Okay. Yeah.
If you were to go further, go through to the end, since the problem doesn't ask you to calculate the current, but since V doesn't change. Well, I guess it will when we...
Right. So for the time being, if we assume that alpha and beta are constants, then this shouldn't have any flux, or it has flux, it doesn't have any time-dependent flux, so there's no current. Yeah. Okay. So now, what it says is, assume alpha is going to be equal to C1t, and beta is going to be equal to C2, okay? So now what we want to do is we want to find the equation for the charge on the plate as a function of time if there is no self-inductance. So what I'm going to do is I'm going to say that there's some plus Q here, some minus Q here, and go around the loop this way, okay? And so when I do that, let's erase this. This allows me to evaluate the left-hand side of Faraday's law, right? So the left-hand side is just going to be the integral of E dot dl, but going around this loop, there's only this capacitor here. I see the positive charge first, and so this is going to be equal to Q divided by C. Okay. Now, to evaluate the left-hand side, I just need to take a negative time derivative of the magnetic flux. And so this is going to be equal to, now I can plug in alpha and beta here, so this is going to be a minus time derivative of H times C1 T times D plus beta D squared, beta is just C2, but ultimately that's not important, divided by 2, okay. So when I take this time derivative, let me make sure I have everything.
You still don't need the dA in the
What's that?
You still need the integral.
What I actually did was, this is really equal to minus partial derivative with respect to time of phi sub b. And I took the phi sub b that I calculated there, and I plugged it in for what the integral is. Yeah. Okay. So now I can take this time derivative here, and what I see is that this is going to give me a minus H C1 times D. Okay. And so this is equal to Q divided by C, and so Q is going to be equal to minus H C1 D times C. Okay. So looking at this, there's actually something that should bother you. Actually, you were talking to one of the TAs about this yesterday. So what bothers you about this?
All right. So it seems like no matter which way you calculate it, you're going to end up with a negative Q, or
not necessarily, but it's getting to that, right?
And if well, okay. So it doesn't quite carry.
It's how do I determine whether this should be positive or negative, right?
And we also had what was really bothering us was that we had a current, and however we calculated it, the current and the charge, they didn't seem to fit with each other.
Right.
We had the current flowing away from a negative charge.
Right. So here, for this particular problem, I had to make a choice here to say that either this was plus Q or minus Q. I could have said this was minus Q and made this plus Q, in which case my answer would be positive. But that doesn't really tell me which way it should have been. I mean, in this case it does. In this case it says that the top plate should be negative, the bottom plate should be positive. But for that problem, the reason why it didn't end up working out well was because if you have a particular function for the magnetic flux, you need to be very careful with making other assumptions. So something that ended up coming out of that problem was that you were forced to have a charge on the plates that was non-zero to start with. Right? Q of 0 had to be non-zero. But there's no reason really why you have to have that. Right? You could have said, well, I don't want there to be charge there, but in a way it kind of forced you to say that. But that's because we assumed that there was no resistance in there. So really, to go through this in a more general fashion, you need to include the resistance of the loop. And that constrains you further, and what you end up having is what we're going to have after the exam, which is a time-dependent circuit. And then it comes down to evaluating the differential equation and matching the boundary conditions. And boundary conditions should always match what your physical intuition should say, that if the current goes this way, the charge should increase or decrease. Right? Okay. Other questions about this one? Okay. So if that's it, I have, like I said, I didn't print this out. I was in a little bit of a rush this morning. But have it here.